Hey guys, so today I'm hoping to do a lecture for you, a little mini one on Chapter 10. If you go onto Canvas, you should have access to Lecture 10, Chapter 10 and 16. We're going to just talk about Chapter 10 today and hopefully make it quick. So Chapter 10, for the readings, again on the first slide you should be able to see the readings and end of chapter problems. The readings will be section 1, 2, and 3, and again hopefully this will be quick. So polymers, if you go to the second slide, polymers are macromolecules. Polymers. When we think of polymers, breaking down the word, we think poly, meaning many. Mer comes from the Greek word for parts. So we're thinking many parts. A polymer is a gigantic molecule made of many smaller parts put together. So polymers are macromolecules, and many of them have formula masses, so molecular mass or molar mass in the thousands. Just for perspective's sake, water has a molar mass of 18 grams per mole, whereas most polymers have molar masses, again, in the thousands of grams per mole. So, polymers consist of many smaller parts. When I think of a polymer, I think first of polyethylene. Polyethylene is the most simple polymer. So, polyethylene. Polyethylene, if I break it down again, poly meaning many, ethylene we should recognize from chapter 9. Ethylene, when I think I think of two carbons. Ethylene. Ethylene, when I see that E-N-E, I also think alkene, meaning there must be a double bond. So when I think of ethylene, I think of this molecule right here. So two carbons, a double bond, and some hydrogens. Polyethylene means there must be many of these ethylene molecules somehow connected together. So I'm going to draw a couple here for you. Again, my ethylene is my carbon-carbon double bond. There should be two carbons because eth for two carbons. So when I think about now how I'm going to put these all together, I think of creating new bonds. I'm going to take this right here and put it there. Now, why did I not leave that bond there? Can anyone see why this might be a problem? Hopefully you see that this carbon has 1, 2, 3, 4, 5 total bonds, which is a big no-no. Yeehaw, got ourselves a Texas carbon. So what I do then is I just take that bond, and instead of having it between these two carbons, I now put it between my two ethylene molecules. Again, I do the same thing, putting these two electrons, having a new bond there. Take these two electrons, and I just keep going. Again, polymers are gigantic. So this right here is only 3 of these ethylene molecules connected together, but polyethylene is likely hundreds of thousands of these ethylene molecules hooked together. So polyethylene is actually also known more commonly to you all as plastic. When I think of polyethylene, again, I think of plastic, and you'll realize quickly how much our lives depend on polymers. Polyethylene. Now, if you look at the bottom of any bottle or any plastic container, you'll usually see something like this. A little symbol, this recycling symbol with a number in it, and some letters on the bottom. This is just a little plastic cup. This one has the letters P-E-T-E. P-E-T-E, if you go to the next slide, you'll actually see all of the different types of plastics and their symbol, their recycling symbol 1 through 6. You should be familiar with that. P-E-T-E, or P-E-T, stands for polyethylene terephthalate. LDPE, low density polyethylene. Number 2, HDPE, high density polyethylene. Again, we are just talking about polyethylene. So another way that I can actually represent this polyethylene is by drawing a big line. Again, I can think of this as a bunch of carbons in a line, a bunch of carbons, and all around it are my hydrogens. So I'm just going to represent this line as my normal polyethylene. Now, again, polyethylene, there are a bunch of different types of polyethylene, so we can actually think that not only do we have this simple polyethylene, but we can start to add functional groups, just like we saw in Chapter 9. When we are talking about polymers, we can actually functionalize polymers to make different uses out of them. High-density polyethylene looks pretty similar to this, where high-density polyethylene just is plain old polyethylene, and I can think, high-density. These polyethylene, these gigantic molecules, because they don't have any functional groups on them, it's just carbon chains with hydrogens all around, I think that, oh, Well, they stack pretty nicely together, and I call that high density polyethylene because they can get so close together. When I talk about all of these polymers stacking together, they can stack pretty closely, which again is high density. A lot amount of stuff per amount of space. Low density polyethylene actually differs in the sense that instead of just plain old carbon chain with hydrogens all around, what I actually see is this thing called branching. So instead of just plain old carbon chain with hydrogens all around, I have carbon chains branching off. So up here, maybe I have another carbon chain branching off. So what I would redraw my big polymer to look like, instead of just a line across, it's going to look something like that, where I've got branches coming off, and we think, well, if I have this big polymer coming into contact with another one, say like that, it's going to be a little bit difficult for this molecule down here to stack with that molecule, and if they can't stack nicely together, then I say that's a low density polyethylene. Again, I say polyethylene because we're just talking about plain old hydrocarbons, but in this case, high density is where I have those long chains that can stack very nicely together, where low density, I have these weird branches that don't allow for the molecules to stack nicely together. So branching actually leads to low density polyethylene. We can actually think of these high density versus low density polyethylenes in our daily lives. So high density polyethylene, when we think of bottle caps, those really hard plastics, those would be high density polyethylene, whereas milk jugs, or, well, really something flimsy, plastic film, something like saran wrap, you could use any kind of soft feeling plastic, or plastic bags, that's a good one. So plastic bags, let me find one. Plastic bags are made of low density polyethylene. High density, again, are the hard bottle caps, something like that, whereas low density would be like plastic bags. So now that we've talked about the basics of polymers and high versus low density, what we can think of again is other types of functional groups that we can put on to our plain old polyethylene. So I'm just going to change this back to the plain old polyethylene, where all I had was a bunch of carbons in a chain and some hydrogens. So one of the functional groups that we can put on is something that we've seen now a whole bunch of times. This right here is my aromatic group. Now, what I have here, again, in a polymer, what I have is a repeating unit. This right here, this molecule where I have C double bonded to C, hydrogen, hydrogen, and an aromatic group, and another hydrogen. This right here is known as styrene, where I put many of these styrenes together, and maybe you've guessed it, I call it polystyrene, where my repeating unit is this styrene molecule. Polystyrene, you might have heard of it, is a polymer where my functional group is an aromatic group. Kind of cool. Polyvinyl chloride is another fun one. Polyvinyl chloride. If I look at polyvinyl chloride, you can probably guess what my functional group would be, a chloride. My repeating unit, chlorine, and chlorine, and chlorine. Polyvinyl chloride, also known as PVC. If you've never heard of PVC pipes, they're those big, thick plastic pipes. So PVC, my repeating unit, has this chlorine group on it, so I see a repeating chlorine over and over again to get polyvinyl chloride. All right, the next one that you see in the slides is polytetrafluoroethylene. So I see something familiar in there. Ethylene. Ethylene, again, this molecule right here, ethylene. The only difference now is it's saying poly. Okay, so let's take the poly off. Just focus on one molecule. Tetrafluoroethylene. Tetra meaning four, fluoro meaning fluorine. So instead of hydrogens, what I have here, tetrafluoro would mean that I have 4 fluorines. Tetrafluoroethylene meaning that my repeating unit is just carbons and fluorines. Fluorines all around. Fluorine and fluorine and fluorine and fluorine. So kind of cool. This is something that might not be familiar to you until I tell you that this is actually Teflon. Teflon is this polymer where I have a bunch of carbons and my repeating unit, again, has 4 fluorines. My tetrafluoroethylene, a normal ethylene, but with 4 fluorines instead of hydrogen. Again, that is Teflon. So the next slide you'll see is a bunch of different polymers, and some cool ones to put on is, for me to tell you, it would be saran wrap. So saran wrap, I have 2 chlorines on my ethylene. I've got 2 chlorines, and that repeating unit is the polymer that makes up saran wrap. PVC we already talked about. Polystyrene, there's one here for adhesives that makes paint, polyvinyl acetate. If you've ever heard of plexiglass, polymethyl methacrylate, that's a cool one as well. So just a whole list of them on there. So with that in mind, this was kind of the lecture on polymers. Hopefully you enjoyed it, and it's kind of cool to realize that almost all of the things around us, plastics, our computers, our phones, our phone cases, our binders, almost everything that we use has something to do with polymers. It's crazy. So just something to think about, and we will start to talk about natural polymers on Monday. Enjoy your Thanksgiving.